Okay, great. Okay, so hello everyone. Welcome to our GDSL Brownback seminar series. Today we have Vanessa Frias-Martinez. Thank for being with us today, Vanessa. She's associate professor at the University of Maryland, where she also leads the Urban Computing Lab. Her research is broadly interested in the interplay between human mobility patterns, social network, and the built environment. And she used a wide range of methods spanning data-driven behavioral models and spatial-temporal data mining. In this talk, she will discuss approaches to how local government and non-profit organizations to understand spatial dynamics of cities and communities, leveraging new forms of data. I won't take much more time because the presentation, the talk seems to be super interesting. So I just want to say that if you want to ask a question, please feel free to use the chat, and we will have time in the Q&A session later. I will get back to that. So without further ado, Vanessa, over to you. Thanks again.
Thanks a lot, Alessia. Let me pull this out. Okay. Okay, so if there's any question, I mean, I don't know how you want to do this, Alessia, if you want to do questions at the end or during the presentation, I'm fine either way. So just let me know.
We generally have the Q&A session at the end, but
Perfect.
Again, it's very much up to you. I mean, if you want to be more interactive, feel free to take the lead. I mean,
yeah, I mean, I don't mind.
Okay.
I know that we have 1 hour and then half an hour for questions. Is that the time that
broadly,
we have?
yeah.
Okay, so yeah, I think that I would be fine either way. So yeah.
Okay.
So just let me know if there's any questions in the chat because I will not be checking it. That's
okay. Yeah, absolutely.
Okay.
Yeah, cool.
Okay. Okay. Hi. Thanks, Alessia, for the introduction. Hello, everybody. Good afternoon. Good morning for me. Good afternoon for everybody else. Okay. So today I'm going to be talking about data-driven decision making for cities and communities. Yeah, it's working. Okay. So, I would like you to think a little bit about the different technologies that you use on a daily or on a weekly basis. Highly probably you use, I don't know, Google Maps to look for routes. You use your cell phone at different locations. You might use Twitter, and you might either have location active, or you might, be tweeting about specific places that you visited. You might be also wearing a wearable when you exercise. And so many of these technologies actually collect location data. And so they might be, telling you and the companies that collect that data for you, things or patterns about how you interact with the built environment. And so generally these types of location within the built environment data are collected by companies to improve their services or maybe for marketing purposes. In my lab, we are interested in understanding how this type of data traces from cell phones or social media can be used to address urban and community challenges. So the approach that we take, we generally start with, different challenges, oftentimes motivated by the Sustainable Development Goals from the UN for 2030. So we've looked into socioeconomic development, we've looked into disaster resilience, human mobility, safety. And what we do is that we embed those challenges within a specific type of built environment. So we've done work that might affect streets, such as walkability, bikeability. We've also do work with transportation systems, with food systems, or within outdoor spaces. The third component of our work is the technology. As I was saying before, we always work with data sets that contain location information about how individuals are interacting with the built environment. And so oftentimes we use data from cell phones that cell phone companies collect. Sometimes we use Twitter data from GPS trackers, from wearables, and so on. And so the approach that we take, oftentimes we start with, a data set that we have from which we extract different human behaviors with respect to a specific type of built environment. And then basically those behaviors within the built environment can then be used for decision-making So if you are, a policymaker or a decision maker in one of these areas, like socioeconomic development, disaster, transport systems, the information that we extract from those technologies embedded, those behaviors embedded within the built environment can then be used as yet another data point in your decision-making approach. Sometimes what happens is that, some of the challenges that we want to work on, for some of the challenges that we want to work on, we don't necessarily have the data that we need to answer those questions. And so what we will do is that we collaborate with the communities of interest to develop technologies that will allow us to collect that data. So for example, right now, we are working on a public transit project in Baltimore City. We are trying to understand what are the barriers that low-income residents face when they use public transit. And so there's no data to model that. And we are developing a tool to collect that data together with, communities in West Baltimore. But generally, this is the approach that we take. I direct the Urban Computing Lab, as Lesia mentioned before, and so our mission is to design, develop, and evaluate computational tools that extract insights from digital traces that will allow us to enhance decision-making in cities and communities. And as you've seen, it's very much focused on both human behavior from a mobility perspective. We've worked on many different application areas. Today, I'm going to be talking only about a couple of projects, but again, to give you this kind of overview of the research that we do, we've done work in socioeconomic development. For example, we were one of the first groups to actually work on socioeconomic maps, predicting socioeconomic information from human behavior extracted from call detail records, from cell phone data. We've also done a lot of work on trying to build migration models, like origin-destination migration models. We've also been working for many years in the area of preparedness and response, mostly working at, predicting displacements during a disaster or understanding or modeling community resilience. We've also done a lot of work on mobility and micro mobility and also on public transit, both trying to understand urban dynamics, but also trying to understand the interplay between income and human mobility. As it pertains to public transit. And then we've also done work in public safety, mostly on systems that predict crime, and also looking into how bias in both the data and the algorithms might affect the crime predictions. So in terms of research areas and methods, I am a computer scientist, and I generally work with either information scientists or computer scientists. And so, the approaches and the methods that we use are very much informed by our background. We generally work with spatiotemporal data collected in cities and communities. Sort of the three thrusts where most of the research falls into, it's either data analysis for modeling and prediction, data bias and fairness, because as you can imagine, many of the data sets that we work with have plenty of bias issues that are very important to understand and analyze. And then a third thread is because, again, many of the data sets that we use have privacy concerns. We're also currently doing work in data privacy as well. And most of the methods that we use are spatiotemporal data mining, machine learning to predict behaviors in space and time, and statistical analysis. Okay, so, again, these are kind of the application areas, the challenges where we've done a lot of the work. I'm just going to focus on one example of basically micromobility and one example of a public safety project. But before I do that, I'd like also to give you like a one slide examples of, projects in socioeconomic development and in preparedness and response as well, so that you have like a broader view of the research that we do. So in the area of socioeconomic development, we've done a lot of work on socioeconomic maps. This has been work in collaboration with the World Bank. And basically, we were looking here at, if we have call detail records from cell phone companies, can we extract different types of both mobility and social behaviors? And are those, or could we use those as predictors of socioeconomic levels for a given region? Okay. And so we showed that using individual data, that is looking at individual mobility and social network behaviors, we could predict socioeconomic levels with F1 scores of 81%. And we also looked at models that didn't use individual information, but rather aggregated information to preserve privacy at the individual level. And we also showed that aggregate models using basically origin, destination, mobility patterns, and social network behaviors also gave us pretty decent, accuracies of 75%. And then in the area of preparedness and response during disasters. We've done a lot of work recently on understanding, predicting displacements during Hurricane Irma here in the US, in 2017. We showed that using either Twitter data or also cell phone data, we could predict displacements, and we could also model community resilience. So, that was one project, but we've also done a lot of work on understanding and modeling displacement during disasters. We've looked into floods in Oaxaca, in Mexico, and Musanze in Rwanda. We've also done work to understand displacements during droughts in La Guajira in Colombia. And some of these projects have been in collaboration with United Nations Global Pulse. But going back to the application areas, what today I'm going to be talking about, it's one project in the area of micromobility. Specifically, I'm going to be talking about predicting cycling safety. And the second project will be on fairness in crime prediction. So I'll talk a little bit about, crime prediction tools, and then I'll delve into, fairness issues and how can we mitigate bias in the data sets that we use to predict crime. Okay, so let me start with the first project, predicting cycling safety. Okay, so I'm sure that many of you are already aware of the benefits of cycling. Cycling is good for your health, and it's also good for your pocket. You can save a lot of money instead of, driving or taking public transit, but please take public transit if you need to go with wheels. But a lot of people don't cycle, right? And the reason why a lot of people, or one of the main reasons why a lot of people don't cycle, it's mostly because of safety concerns. This is an old statistic from the CDC Injury Center from 2013 from the US. There were around 500, like 500,000 cyclists injured and around 700 deaths. Now, generally, when cities, again, this is in the US, I understand that, in Europe, in different countries, the approach might be different. So, I'll be happy to discuss this. But generally in the US, the safety measures that are put in place in cities to create safer cycling environments are oftentimes based on crash numbers, okay, on accident numbers. But we all know that these numbers are incomplete. They don't reflect all of the accidents that happen. Many of the accidents go underreported. They are not reported basically because nothing happened, but could have happened, right? And so in this project, what we tried to do was push this sort of using crash numbers as a decision-making point to also incorporate safety perceptions. So, crash numbers might be one piece of information that you can use, but also we should be understanding like how we see that individuals perceive that street as being safe or not. Now, we are not the first ones to propose this. There's something, it has different names. I'm going to call them cycling safety maps in this presentation, but basically a lot of cities in the US compute these type of maps. These type of maps basically represent each street segment. They color coded. In this case, this is a cycling safety map for Silver Spring, which is a small town near College Park, near where my university is located. And so, they use three colors. The light blue indicates that it's very safe to cycle in there. The dark blue, it's okay. And the red indicates that you should cycle, with care. Now, these maps are generally used either to identify locations where, cycling improvements could be incorporated, but they are also oftentimes used to evaluate connectivity. That is, if you want to look into how one neighborhood is connected to, say, a school or a shopping center by safe cycling routes for equity purposes, you can also look into that and basically model or understand whether there are certain neighborhoods that have wider coverage of safe cycling routes. So, these maps are important for decision-making and for, understand like what are the areas where cycling safety measures should be put in place. Now, the way these maps are computed currently is as follows. So they are generally based on associations between street attributes and cycling safety perceptions. Let me walk you through how these two pieces of information are gathered and how they are used, how they are associated. So in terms of the street attributes, departments of transportation generally look at different metrics, like, for example, traffic speed, traffic volume, frequency of parking turnover, because, because of dooring issues, like someone might open the door while you're cycling. And so generally these street attributes require expensive sensors that obviously cannot be available in every street. Some departments of transportation in the US also use video recordings. They put cameras at specific intersections of pieces of street. And the issue with this approach is that they are expensive and they are generally not scalable as a result of its cost. And it also generates a lot of privacy issues because you have basically cameras, recording cyclists. And then on the other hand, the way they use this information is that having information about traffic, having information about speed and so on, these metrics are associated to cycling safety perceptions, basically based on either logical intuitions. For example, if you have more cars, people might feel less safe. And generally, these intuitions are based on qualitative studies, basically small-scale studies that have been done in different cities and that whose generalizability has not been validated. So basically, you might have a small study from how cyclists perceive safety in an intersection in Denmark, and then those studies are just translated to Silver Spring in Maryland without any type of validation. And so in this project, our main aim was to propose a new approach to how cycling safety maps are computed. And so we tried to answer two research questions. The first one was whether we could find more affordable and scalable attributes for cycling safety. That is, instead of putting cameras that will record everything, instead of the need to put sensors in the streets that will record metrics that are currently used to understand cycling safety perceptions, can we look for information that could be more affordable and that, that as a result could be gathered for many more cities, not just for those cities that could actually afford the sensors. And so as a solution for this, what we proposed was exploring the use of open datasets and open street maps as a source for street attributes. Our hypothesis was that if we can actually use data from open datasets and from open street maps as to characterize the street attributes instead of putting expensive sensors, then we would be lowering the bar of which cities can actually compute this type of cycling safety maps, right? Because open data repositories around or over 2,600 cities worldwide have this type of repositories. And if it's just information from OpenStreetMaps, around 4 million small to mid-sized cities do have OpenStreetMaps information, right? So if instead of using sensors, we were to use information extracted from these data sources, many more cities worldwide could be able to compute this type of cycling safety maps. The second research question that we wanted to answer in this project was, because again, these associations between street attributes and cycling safety perceptions have not been validated. Our question was, can we actually formally validate the association between the attributes that are supposedly predictive of cycling safety perceptions and the cycling safety perceptions themselves? And so what we did here was basically crowdsource cycling safety perceptions, meaning that, we recorded cycling videos, and I will walk you, through the different steps in a second, but we basically recorded cycling videos and asked cyclists to rate how they perceive safety in those videos. And then we built machine learning models that could basically predict cycling safety perceptions from street attributes. So this is the framework that we designed, right? It has three main components that I will, give details about in the next slides. The first component is the perceived cycling safety attributes. So we used open data portals, we used OpenStreetMap information to basically extract segment level features. The second component was that we recorded videos. We asked cyclists to provide labels for those videos, like cycling safety perception values. And then we used those ratings to basically, as a ground truth for our models. And then the third component is we built models that, using the segment level features that we had extracted from open data portals and OpenStreetMaps, and using the ground truth labels from cyclists, could predict one from the other. And I'm going to walk you through an example that we worked on for Washington, D.C., because we are just 20 minutes away by metro from Washington, D.C. Okay, so for the first part of the framework, the perceived cycling safety attributes, again, as I said before, the idea here was to look into street segment level features that would characterize street attributes. The street attributes that we looked for were informed by qualitative research into, what types of attributes might influence cycling safety perception. And so, for example, some examples are characteristics of the built environment that can be extracted from OpenStreetMaps. So, for example, the presence of cycling facilities has been related to your perception of safety, to the perception that cyclists have of cycling safety. And other, for example, elements like the social fabric has also been identified as influencing your choice of cycling route. And so we could extract something like, for example, crime rates from open data sets. So, we did these two types of features, built environment features and social fabric features. For built environment features, we mostly work with three different types: road network characteristics, that is the types of streets, classification of streets, the presence of different types of cycling facilities. And then we also used graph-based road network features. Maybe these are the ones that are less intuitive. So let me just give you like a one-slide summary of what we mean by this. So there's a lot of work on basically transforming cities into graphs. And so, you could have like a primal graph in which an intersection is a vertex, and the connection between and the segments themselves are segments of the graph. You could have the dual graph where a segment is a vertex and the intersections are segments of the graph. The idea here is that you look at a map of a city and you see it as a graph with vertices and edges, right? And so you can compute the centrality of those vertices, meaning how important different street segments are with respect to the whole street network in a city. I will talk about this a little bit more further on, but our hypothesis for using these type of features was that highly central segments could potentially be associated to high traffic conditions. And we think that that's, how the model is actually using these features. But I will talk more about this in a while. And then the second type of features that we extracted from open data sets were social fabric features, things like crime rates, different types of points of interest that might motivate cycling traffic in different directions, a bicycle crash information, 311 requests, like many cities have 311 request systems where we mostly focused on looking into street conditions, like for example, requests for street lights needed to be changed that could inform about cycling at night or the perception of safety for cycling at night. And we also use parking and moving violations as well as an indication of potential cycling safety. Again, all of these features are motivated by qualitative studies that have identified these through focus groups with cyclists. So specifically for DC, these are the different features that we consider: 63 different built environment features, including 11 road network types, 39 graph-based metrics, and 13 cycling type facilities, extracted all of them from OpenStreetMaps. And then for social features, that's a list of social features that we considered. For the machine learning model, we considered both monthly averages across these types, but also monthly averages per type. So we would have either 6 features or 148 if we are to consider, the different types within each attribute. Okay, so now that's the first part. For each street segment, we have, characterized or we have extracted different street attributes from various open data sources. Now, the second part is the collection of ground truth. So when you train a machine learning model, a supervised machine learning model, you basically have a set of characteristics for each data point. In our case, the data points are street segments. We also need a ground truth to train the model. How did we collect ground truth for street segments? So let me explain you the model that we built. This was a project that we did in collaboration with WABA, which is Washington's Area Bicycle Association. So it's a cyclist association that is based in DC, but they're cyclists from, sort of all over the tri-state area around DC. What we did was we recorded cycling videos in Washington, DC across many street segments. And then we built a web page where we invited cyclists to watch those videos and provide cycling safety perception ratings. WABA, the Washington's Area Bicycle Association, they helped us promoting the website in various cycling events that they organized throughout the year. And we basically collected cycling safety perceptions from cyclists. This is how the webpage looked like. So let me, rather than showing you the slide, let me show you the actual webpage that we used. Okay, so this was the webpage where cyclists landed once they decided to participate. So the first thing that they need to do was provide the email, because we would then give to all participants a gift card. The first question that you had to fill out was, how confident are you as a cyclist? Are you a fearless cyclist, confident, interested, or reluctant? I'm going to say I'm a confident cyclist. There was then an optional survey where we asked different socioeconomic and demographic features, and also, different questions about basically frequency of riding and so on. I'm going to skip it if I can. Yes. Okay. And then basically what cyclists had to do was go through these videos and look at the video and basically provide a rating from 1 to 5. Let me mute it. So these are short 20-second videos. Okay, so after watching it, basically cyclists needed to rate it from 1 to 5, from too dangerous to very safe. So, and then basically provide a reason for this rating. So maybe I'd say that, I felt that it was, I don't know, maybe fair, and maybe I missed having a bike lane, for example. We also ask for familiarity, like cyclists oftentimes cycle, in DC, and we use this familiarity also as another feature as part of the machine learning model, but this was not a compulsory question. And so after doing that, they could basically save and continue rating as many times as they wanted. So you would have here another video and rate again. And once they were done rating, they could basically say, okay, I'm done. And then basically you would see here the map with the ratings from everybody, from all the cyclists that had participated at the time when you were filling this out. Okay, so we did this, and basically, let me give you some statistics about participation. So we got around almost 1,500 different ratings from 159 participants. We had, typical participant behavior. So we had some very enthusiastic raters that rated 40, 50, 60 different videos, but on most of them, the majority, like 64%, rated between or up to 10 videos. Then as well, when you have this type of rating from 1 to 5 approach, there's been a lot of studies, for stars ratings or this type of number rating. This bell curve is very typical in that a lot of users will rate it as the middle number being the rating that they provide. And we generally have fewer numbers of ratings for the extreme cases, from very safe to, to very dangerous. And then in terms of reasons behind those ratings, we observed that there were, the most frequent ones were bike lane design or lack of it, the traffic conditions, dooring in DC, many of the bike lanes are terribly designed. And so there's a lot of dangers of parked cars opening the doors and, hitting a cyclist. But there were also concerns around, the social fabric, as we had expected in terms of neighborhood security. Of course, these features might change depending on the city where you run these, but the beauty of this platform is that you can actually record videos and do a similar thing for many other cities. Just to give you an example of very dangerous, very safe, this is, some of the ratings, some of the ground truth labels that we collected from cyclists. It's an obvious example. Okay, so now we have a street segment features. We have ground truth labels for those segments. How do we predict cycling safety perceptions from street segments? So, well, first of all, we frame this as a classification problem where we have 5 different classes, and we have to predict, what's the class for a given segment based on the street features that we extracted from open data sets. However, there was a lot of engineering effort behind this, mostly because, cyclists were rating videos, and videos could have different segments, and some of those segments in the video could just show like part of the street or all of the street. So basically for each street segment, we might have ratings from multiple cyclists, but we might also have ratings from cyclists that only looked at, part of the street, or that looked at, at all of the street. And so we had to do a lot of weighting of, the different ratings that cyclists provided, averaging both in terms of, averaging across cyclists, but also taking into account the percentage of the street segment that was shown in the video. And then, once we have that data set ready, we applied MR for feature selection, and then we did a 5-fold cross-validation, basically, train with 4 folds and test with the 5th fold and repeat it 5 times. These are the classification results. We explored different supervised models, SVMs, decision trees, bagging, random forest, gradient boosting, and XGBoost. And what you can see here are basically the results for the different types of features that we were considering. And the baseline is just, just consider all the ratings to be the average value. And so what we can show here is that using both built environment features and social features gave us the highest F1 scores. The value on the left-hand side is the F1 micro. The value on the right-hand side is the F1 macro. So the reason why we showed both is because if you remember, we had a sort of a bell curve in that we have a smaller number of ratings for the extreme classes, the very safe and the very dangerous. And so, generally F1 score macro allows you to understand the performance for the classes for which you have a lower number of data points. And so what these numbers are telling us is that, the accuracy or the F1 score is 65%, but that we are performing worse when, we consider the number of samples that we have for the extreme cases. But interestingly, to me, the most interesting result of these experiments was actually that only using built environment features, we obtained a 0.62 F1 score, only using built environment features. Okay, so we are able to determine if a street segment is from 1 to 5, only using features that we extract from OpenStreetMaps. And as I mentioned earlier, OpenStreetMaps are available for around 4 million cities worldwide. So, just using these features that are openly available, we could have a fairly decent, approximation of how cyclists perceive cycling safety once we collect, cycling safety features for a given city. And only using social features gave us kind of worse results, but still around, the 60. We also tried different things, like tried to improve those results. For example, again, because we had fewer samples for classes 1 and 5, we tried some over and under sampling with this mode, which improved a little bit the F1 micro. We also looked into more unsize statistics, basically looking into the spatial correlations of some of the features that we used. And in fact, many of the features, I'd say most of the features that we were using at the street segment were spatially autocorrelated. So what we did was enhance the features of a given segment with features from nearby segments, like within 150 meters, I think that we consider a radius. And that also improved a little bit the macro scores, meaning that we were doing better for classes for which we had a smaller number of samples. And we also use things like, for example, cycling experience or familiarity with the streets to understand, cycling perceptions. That also improved a little bit the macro values. Overall, the 5-class experiment that we trained for gave us the best macro and micro and macro scores were 66 and 48. So, 66 for the score. But if we were to consider a 3-class setting, remember the example that I gave you at the beginning for Silver Spring, where they only had 3 levels. If we were to only use 3 levels, our scores would be around 88, which is a very high score to understand, whether a street segment is considered safe or, average or dangerous. So let me show you, basically this, we trained this model with features from a few street segments in Washington, D.C. Obviously, we could not collect videos for all of the street segments, and that's, you know, the main purpose of having this predictive approach, that you can collect videos for a small number of street segments in D.C., and then you can predict values for all of the other street segments in the city. And we know that the accuracy for the F1 score was 88 if we consider 3 levels, 66 if we consider 5 levels. And so, you know, applying this machine learning method to all of Washington, D.C., we can actually predict cycling safety perceptions for all of the street segments in the city. So let me show you this map. Okay, so this is a map of D.C. We considered like 5 different cycling safety perceptions, from very dangerous to very safe. Obvious things, I mean, some of these red things that you see here are highways. This red thing is just a huge park that we have in DC. It's called Rock Creek Park. And then just to give you, you know, let me go. I always go to my neighborhood because I cycle a lot, and so I know it better. And so, for example, one of the interesting things that we saw was that if you see, this is 15th Street, this is 17th Street, both these streets have, and also U and Q, all of these streets have cycling lanes. And so, you know, it was very interesting to see that most of these segments were predicted as being, you know, safe or very safe. And this lane, 16th Street, does not have a cycling lane. So, you know, some of these results make sense. And then, you know, if you are a decision maker working in DC, you can also click in any of these street segments. It will tell you the address, and it will tell you what the machine learning model predicted. So in this case, you know, these are the different certainty values. So, you know, it's dangerous and with an 87%. It could be normal 5%. So I mean, it could be very dangerous with a 5% probability. So this is definitely a dangerous, you know, street segment. Okay. Okay, so, you know, what can decision makers do with this? So basically, this provides a detailed map to assess cycling perceptions, cycling safety perceptions at the street level, right? So not only crash numbers, but also how is it that cyclists perceive cycling safety, you know, in these different street segments. It could also, you know, inform of places where they might need to go and take a look, because apparently cyclists perceive a specific area as being very dangerous. It could also inform of, you know, cycling safety at the trip level. If you want to go from point A to point B, you know, you could basically look at the cycling safety perceptions throughout those routes. And of course, because this is a machine learning model, we can also look at some of the features that were highly predictive. For example, you know, closest centrality of the segment was highly predictive. And again, the hypothesis here, I mean, closeness centrality means that the segment is very central in the city graph, meaning that if you want to go from point A to point B in the city, many of the paths go through that segment. And we think that the reason why this is a very important feature in the prediction is because it might be mimicking, you know, traffic, like traffic measures, a measure of how much traffic there is in that segment. The presence of cycling facility was also a very important predictor, and crime rates were also a very important predictor. Again, many of these predictors might change depending on the city, and we could figure that out by training new models. Okay, so that's for project 1. Let me move on to project 2, which focuses on fairness in mobility-based crime predictions. So we are completely changing gears here. Okay, so the main motivation for this project was basically that there is a lot of work that has shown that crime prediction tools output unfair results for certain social groups. Work in the US has shown, for example, that crime prediction tools provide less accurate predictions for Black neighborhoods. And so the main rationale for this project was to understand whether we could build crime prediction tools that are fairer, that provide, you know, fairer outputs across social groups. The focus is on mobility-based crime predictions. And so let me walk you, you know, through the different steps in this project. But again, the motivation is that if we want to build crime prediction tools and we want to have fair predictions. And, we can measure fairness in different ways. In this case, we focused on basically having equally accurate results across social groups. Then we basically need to understand how to do that or how to mitigate biases that might be present in the data set. But before I do that, I'm going to explain a little bit or give some background in crime prediction tools, then in crime prediction tools that use mobility data, and then I will start talking about fairness and data bias. So crime prediction tools are tools that are used to predict areas in a neighborhood where crimes might happen at a particular time. Okay, there's in the US, there's a very well known crime prediction tool, which is called PredPol, which is currently used by around 16 police departments. One of the largest ones is Los Angeles Police Department. There's another one like Crime Stats, but PredPol is definitely, the most popular tool. Crime prediction tools generally use historical crime data from the past 2 to 5 years to predict future crime instances. And then within crime prediction tools, there has been some work that actually incorporates, besides historical data, it also incorporates mobility data. Okay, under the premise, or basically based on a crime theory called opportunity makes the thief, that says that areas where there's higher presence of individuals might attract more crime. And so there's various groups that have actually showed that incorporating mobility data into crime prediction tools improves the accuracy of the crime predictions, mostly based on the fact that, information about hotspots or highly frequently regions are associated to crime incidents. So basically, what these groups have showed is that areas where there's a lot of people present, what I will call from now on hotspots, are basically predictive of crime volumes. This has already been shown. We are not the first ones to do this. Now I'm talking about hotspots. Hotspots are defined as, regions that are frequently visited or more visited than other regions in a city. And hotspots can be computed in many ways using geolocation data. For this project, we focused on hotspots, or on understanding what areas are more visited than others, using call detail records, using the records that telecommunication companies collect, for billing purposes. Call detail records basically are not GPS data. They only have location information about the cell tower where the cell phone was at a specific moment in time and the time when that location was collected. These collections can be collected either when the person uses a cell phone or, with a certain frequency, because telecommunication companies oftentimes ping cell phones, not necessarily only when, service is offered. And so what I'm going to show here is how mobility-based crime prediction models work, okay, and specifically the design for the one that we used to understand and mitigate fairness issues. So generally, mobility-based crime prediction models using call detail records, generally they start with just, computing, okay, how many individuals were observed at a given place at a given moment in time. So for example, here I'm showing for each hour color-coded Voronoi polygons. Each Voronoi polygons represent the number of people that were seen there at that time. And Voronoi polygons are just used as an approximation of the coverage area for cell towers. This is, kind of what's done in the literature by, researchers using cell phone data. What we do then is that generally crime prediction tools work at a grid level, not so much at Voronoi polygon level. So the second step is move from number of individuals observed there, or footfall, to interpolate, that footfall to a grid. So, that's the second step. Then the third step is moving from hourly footfall to hotspot detection. Like, how do you define a hotspot? There's different measures or approaches to extract hotspots. Like, how do you identify that an area is more visited than others? The simplest one would be, okay, we have, this is the average value. If it's 1 or 2 standard deviations above that average value, then we consider that to be a hotspot. For this specific project, we used a method called Lubar method, which is based on the Lorentz curve. And we used it because it provides a threshold or an upper limit for the number of hotspots. So basically this method determines the maximum number of hotspots that could be there. And so, we wanted to work with this upper limit, but you could use any other approach. You can detect hourly hotspots or permanent hotspots. And then basically, once you have these hotspots, what we do is that we extract different features about those hotspots. Specifically, you can work with measures of scale, sprawl, or compactness, right? So you can measure how many hotspots you have at a given hour. You can measure the area covered by those hotspots. You can measure whether it's, mostly a city with like a one hotspot area, or whether it's like a polycentric city. You could measure like compactness metrics, like, the proximity between those hotspots, moment of inertia. So, there's different metrics that we considered for this project and that have been considered by others before us. And basically, once you have those features for hotspots, you can just, put it together with crime data and try to predict crime volumes from those hotspot features. That's the way mobility-based crime prediction works. You have specific features for the hotspots or metrics for the hotspots, and then you try to predict crimes from those metrics. However, as I was saying before, the main contribution of this project was not in building a crime prediction tool that uses data for mobility, data, but rather to understand to identify, fairness issues that these tools might have, and to mitigate or try to control for or correct for those fairness issues. So let me walk you through what we did exactly here. Okay, so as I was saying before, so some crime prediction tools have been shown to have diverse or actually unfair performance for certain protected attributes. So again, some crime prediction tools have been shown that, the accuracy of the prediction is worse for example, Black population. And so for this specific project, we focused on, there's many metrics of fairness. We focused on fairness measured as parity across protected groups. And by parity, we mean that we wanted to have similar performance across groups. There's very little work on how to actually address fairness issues in crime prediction tools, and not at all, like zero work before publishing this paper on how to address fairness issues in mobility-based crime prediction. Now, the reason why mobility-based crime prediction tools might output unfair results could be various, right? I mean, you could have different performances across groups because, the data that we are using is biased. Think about how crime data is collected. A person has to report the crime. The policeman or policewoman has to record the crime. Sometimes crimes are not reported. Sometimes crimes are not recorded. So there's a lot of bias that could potentially go into the crime data sets that we use. The mobility data that we use could also be biased. Not everybody has a cell phone. There's sampling bias in the data sets that we generally use. But the diverse outcomes across social groups could also be used to the fact that the predictive algorithms themselves are amplifying the bias in the data. So, bias or, lack of fairness in the predictions could be due to many things. We are working on all of these different aspects. For this project, we focused on lack of fairness due to bias in the crime data. Okay, so we framed the problem as, lack of fairness potentially due to underreporting. And again, the crime data sets that are generally used when crime prediction tools are evaluated are crime data sets collected by police departments, and those crime data sets don't cover all of the crimes that are happening. Community does not always report crimes, and the police does not always record those crimes. Just to give you some examples, there's a lot of work on crime underreporting, like qualitative studies. It's been shown that racially mixed communities are less willing to report crimes. So if you look at volume of crimes from communities that are racially mixed, generally the number of crimes that are reported is lower, although there's a similar amount of crime. Oftentimes, it's been shown that women face barriers in reporting sexual related crimes. So there's definitely underreporting in that front as well. And oftentimes what happens is that police are more willing to record in their databases some types of crimes. And, for example, it's been shown that there's more recordings if, the crime report comes from middle-class groups than from low-income individuals. And so the focus of this project was, okay, I mean, we know that many of these crime prediction tools are outputting unfair results. This is probably in part due to the biases that we have in the crime data. Can we propose a crime prediction tool that uses mobility data that mitigates the bias in the crime data? And so our approach for this was to basically incorporate in the crime prediction model, we wanted to incorporate domain knowledge about underreporting, right? So if we know that race might play a role in how people report crimes, if we know that it might also play a role in how the police record crimes, if we know that gender might also play a role, can we incorporate those features into the prediction model? And now we hypothesized that by doing that, we could improve the fairness of the outputs of the crime prediction. Okay, so we proposed a model which we call the Burke model, and it's basically a hierarchical Bayesian model. Now, the main idea here is that, what we observe, well, like when we look into the crime data sets that are used by, researchers that are working on crime prediction tools, they generally use this what we call CI value, which are the reported crimes that are, in the crime databases. However, we argue that that's not the actual number of crimes that's happening, that the actual number of crimes is something that we call YI, okay? And that those crimes happen at a crime occurring rate that we call lambda, okay? We don't know this YI, we don't know the true number of crimes, but we know that it's definitely not the reported crimes because there's underreporting and under-recording issues. We model the reported crimes, CI, which are the ones that we extract from the databases as, again, a Poisson model, but in this case, it's the crime occurring rate discounted by our reporting rate. This reporting rate is also something that we don't know, but we know that the reporting rates are influenced by things like, for example, contextual features, by your gender, by your race, okay? And so if we consider these two models of how crimes are actually generated in a city, we then defined two linear regressions to model the crime occurring rate and to model the crime reporting rate. We argued that the crime reporting rate could be modeled as a regression based on contextual underreporting features, again, age, gender, poverty rates, and so on. And we argued that the crime occurring rate could be modeled based on hotspot features, again, based on the on crime theories that determine that, presence of individuals is associated to crime, okay? And by basically, fitting this model, we could basically identify the two hidden variables that we don't know anything about, which are, the true volume of crimes as opposed to the reported crimes. And on the other hand, and on the other hand, the pi value, which is basically, what's the reporting rate. Okay, so the way we, Okay, so the way we did, we worked on this model, basically we started with the mobility data, and we considered both hotspots features and the underreporting determinants. We then built the Burke model that we proposed, and we also built other, what we call underreporting and aware models, which is basically models that take into account the underreporting determinants, but not embedded as an underreporting process, but rather just as features themselves. And then obviously we can then extract, the actual predicted volume of crimes, which is YI, and we can also extract the predicted number of crimes, CI, and the same thing for the underreporting and aware models. The difference between C and Y is that this is the predicted number of crimes based on the crimes that we extract from the databases, okay? Whereas Y is the actual number of crimes that are not, including the ones that are not being reported. There's no ground truth for this value, but I will show you how we compare that to the only statistic that we found that, shows promising results, but I'll talk about that in a while. So how did we evaluate this? Okay, so basically we used cell phone data from 2009-2010 for around 1,400 municipalities in Mexico. We also used official crime statistics that included both property and violent crime, and we used the set of underreporting determinants that I mentioned before. The hierarchical Bayesian model the Burke model was fitted basically with all the data that we had, with the hotspot data, the underreporting data, and the crime data using MCMC. And in terms of underreporting and aware models, we used random forest, bagging, and SGBoost. Again, the difference between our model and these models is that these models are not modeling the underreporting phenomena, but rather are just inputting domain knowledge underreporting features. And we tested these models using 5-fold cross-validation. So, 4 folds for training, 1 fold for testing. Now, as I mentioned at the beginning of the presentation, so there's different measures or approaches or definitions of fairness. For this project, we focused on achieving approximate parity, meaning similar performance across protected groups. For this specific project, we considered 2 protected groups or protected attributes. One was income and the second one was indigenous population, meaning we want to look at how crimes are being predicted across income groups, across indigenous population, and we want to see if the performance is similar across all of them, or if, like in previous work, lower income or maybe, counties with higher indigenous population suffer from worse predictive results. For the protected attributes, we basically used income, considering 4 income groups that were extracted from basically a census that the Statistical Institute in Mexico does every 5 years. So we took the one from 2010, which was from the time from when the CDR data also was. And we also considered 4 indigenous populations groups. So basically municipalities that did not have indigenous population at all, municipalities that had less than 40% with population less than 5,000, municipalities that had less than 40% indigenous population with more than 500 residents, and then municipalities that had more than 40% indigenous population. The fairness metrics that we used, again, focused on parity. We used 2 metrics, the root mean square error parity and the mean difference parity. For the first metric, what we want to do is basically we measure the difference between the predicted value and the actual volume of crimes. And we look at, how different these 2 are. The objective is that the root mean square errors across income groups and across indigenous percentages are similar. The second fairness metric that we looked into was mean difference parity. And in this case, what we're looking into is looking into the absolute numbers of crimes that we predicted. And the idea here, the fairness metric here, basically tries to see whether the difference between a volume for one group and all of the other groups is similar across groups. So basically the numbers that we are predicting are similar across groups. And my battery is running. 1 second, I'm going to plug my computer. Give me 1 second, please. Okay, here I am. Sorry about that. Okay, so those are the 2 metrics, right? So, we are going to train our Burke model and train all the other baseline models that we considered. And we are going to be looking at how well the Burke model does compared to the baseline models, both in terms of root mean square parity and in terms of mean difference parity. Okay, so what I'm showing here, these are the different models that we use, and these are the different income groups that we considered, right? So this is just for property crimes. We consider different types of crimes. The results are in the paper. I'm just going to describe like one result here. But basically, what you can see, each of the numbers here, what these represent is the root mean square error metric, and the number in parentheses is the normalized value by group average, right? And so, what we can observe is that the model that we propose the model that incorporates underreporting, basically the model that takes into account that the way crimes are being reported depends on specific social and demographic features, was the one that had the lowest root mean square errors for each of these income groups, except for income group 3, in which it was a little bit higher, right? And so what we posit here is that the Burke model was able to decrease the root mean square errors, and so it's pointing to improved fairness. Okay, I mean the accuracy is going to be similar across group, but it's pointing to improved fairness. Basically, if you look at the errors here, the errors that this model is making with respect to all of the other models are lower, right? And across, again, most of the groups except for ICQ3. The second metric that we looked into was normalized mean difference. Okay, in this case, we are comparing the volume of predicted crimes with respect to the actual volume of crimes in the data sets. Okay, so in this case, we can actually disaggregate this a little bit more. We can look at these C values that all of the models predict, including the Burke model. But we can also look in the Burke model, we also have these what we are calling the actual number of crimes for which we don't have any ground truth, okay? And so what we actually showed here was that the Burke model that incorporates this underreporting process had the best normalized mean difference across income groups. Okay, so again, what this means is that the volumes of crimes that were predicted across different income groups were more similar than those predicted by any of the other models. This is taking into account what we are calling, again, the actual volume of crimes for which we don't have a ground truth. We did similar analysis for property crimes and indigenous groups, for violent crimes, and generally they showed similar results in terms of fairness and performance. So how can these be models? How can these models be used for decision making? So what we did to show some examples from a decision making perspective, or to offer you or to incorporate new data points for police departments to analyze, what we did was we took all the data we had. We fit the Burke model and we analyzed two things. We analyzed the true volume of crimes with respect to the reported crimes, and we also show how we can analyze the role that different features play in underreporting. So let me walk you through these two things and then I'll be done with the presentation. Okay, so the first thing that we did was look, what I'm showing in this plot, what you have on the x-axis is the reporting rate, right? So I mean, what we are doing here, what we're showing here is that if you look at this number around here, we're showing that around 94% of all the municipalities have less than 10% of the violent crime being reported. Okay, so the way we're doing this is that we are comparing the actual volume of crimes that our model is approximating with the crimes that we have in the data sets that we are using. Right? Again, this Y value is a value that, it's not a ground truth, it's nowhere because it's hidden under reporting. But what we show is that with our numbers and our model, 94% of the municipalities are actually reporting less than 10% of the crime. The only approximate thing that, I don't know how to actually. So I want to remove this so live, but I don't know how to remove this. Escape, no. Does anybody know what do I need to press to remove this from here? Nobody. Okay.
The bracket?
Okay, I'll move it up. Fine, that works. So basically, this, as I was saying before, what this result shows is that looking at the actual volume of crimes compared to the volume of crimes that we extracted from the data sets that researchers generally use to build these models, what this is telling us is that less than 10% of the violent crimes are actually being reported. The only kind of ground truth that we found was from a survey, again in Mexico for the same similar time period, that revealed very similar underreporting rates. So what they did was just by asking, it was like a survey where they asked for, what crime had you suffered in the past year. And so they recorded those numbers and they compared those against the actual, crime databases. And they also found a similar percentage of underreporting crime rates. Okay, so again, there's no ground truth. So this is the only comparison point that we could find. But you know, what our model can do is, one, it can approximate the actual volume of crimes that could be used as an alternative data source for crime data, so that we can take into account, you know, the actual number of crimes that are happening. And that would partially remove, what our results are also showing is that by considering those numbers, that could partially remove some of the bias in the data sets, because we are showing that, you know, the fairness or, you know, the fairness metrics that we are using actually improve with the model that we proposed. And then the second thing that we can do is that, because if you remember the Burke model, these are based on linear regressions. So, you know, the rate at which crime happens and the rate at which, you know, crimes are reported are based on linear regressions. So, you know, the true crime prediction, when we compute the actual volume of crimes, that depends on hotspot features. So we can look at the role that hotspot features play on crime occurrence. So what I'm showing here, for example, is that if you look at the number of hotspots or the area of the hotspots, those are positively correlated to the volume of crimes. If you look, for example, MComp is the compacity. So, you know, the more spread the crimes are, the more spread the hotspots are, the lower the volume of crimes. But also we can look at, you know, the linear regressions for the crime reporting, which are based on the underreporting features. And for example, you know, what this coefficient tells us is that, you know, the higher the poverty rate, the lower the number of reports that, you know, we will have, which is coherent with the literature. And so basically, you know, as I was saying before, this Burke model can be used to quantify how bad the underreporting phenomenon might be. Again, there's a lack of ground truth in here, but if there's countries that are computing like similar surveys to the one that we used for Mexico, that could be a really great contribution. It also allows us to understand the role that socioeconomic features play in the underreporting, but it also allows us to quantify the relationship between crime and hotspots features. Okay, and I just want to finalize by saying that, you know, this is work with many collaborators and many students, and, you know, these are most of them. And thank you. I'm done. I'll be happy to take questions.
Thanks a lot, Vanessa. That was absolutely brilliant, very interesting project. So yeah, again, anyone who has any question, please feel free to use the chat or raise your hand if you want to. I will give you space to ask your question directly. So while people think about questions, I do have a few actually. So, well, the first one is on the first project, the one on cycling. You've crowdsourced perception of safety, and I saw that you did have some initial survey to get some demographic characteristics of the people. To what extent well, I mean, how much results did you get from that, and so was that usable in a way to also, you know, somehow consider safety from different perspectives? Because I mean, I'm just thinking that there might be some relationship between, let's say, gender and perception of safety as well, or anything else. I don't know if you found anything on that.
Yeah, that's a great question. So yeah, so we added the survey, but very few people actually, you know, provided enough details on the survey. That was the original idea, you know, incorporating other features as well. The same way we incorporated, for example, whether you were familiar with a Griven Street segment, or, you know, whether it was familiarity, and then your cycling safety, you know, your cycling level, basically if you were confident cycling or things like that. Those were metrics that we were able to incorporate because everybody provided them. But we decided in the end not to make the survey compulsory, and then the number of responses was so low that we couldn't use it in the model. But yeah, that was the original idea.
Okay, yeah, no, because that would also be interesting too.
Yeah.
But I'm assuming that with the results that you found, actually, you could generate cycling safety maps based on the feature that you get with the OpenStreetMap from basically everywhere, right?
Yeah, so I mean, we would need to collect ground truth, right? So the way we train the models, there's two ways of going about it. You could just, take our model, take OpenStreetMap data from any other city and use our model to predict those. That would be, the kind of the shortest route. However, if we do it that way, you'd kind of be assuming that all of the perceptions are transferable, and it might be the case that they are not. So that's another idea that we had, but again, we ran out of funding. But another idea that we had was trying to run it in 2 or 3 more cities and try and see whether the model was actually transferable or not. Our hypothesis was that at least within the same country or the same state, highly probably it would be transferable. But then there's countries that take cycling safety like and there are different approaches, and so it might not be for like transferable worldwide. But yeah, so I think that within US communities you could fairly easily just extract the OSM data and try to predict cycling safety. I think that would be a fair approach across different types of countries. That's something that I think that should be tested.
Well, good to have other work to be done, right?
Yes.
Fine. So again, on generalizability, I was also thinking that this is more about your second project, because I found very, very interesting this. I mean, I'm not an expert on crime data, crime statistics. It's definitely not my field, but I found very interesting that underreporting might affect that much statistics on crime. I was just wondering, so, and you basically said that there are some socioeconomic determinants in underreporting. So I was just wondering again, how much those determinants are generalizable across other countries, or there might be different sources based also on different culture, let's say level, racism, things like that.
Yeah, I mean, the second project is very much focused on a US context, I'd say, in which, the relationship between race and police departments, I mean, it's evident that it's, especially, with the minority populations, is not a good one. And so the data that we are inputting into the models is biased in the sense that, crime volumes in counties that have high percentages of minority populations are much higher just because they get recorded more, right? And so then basically, a machine learning model can only do what the data that you input into it does. And so if you're inputting something that's biased, then your output will be biased. I think that in other non-US contexts, the relationship between communities and police might be different. And so, that's something that like the bias could potentially have a less impact or more, I don't know, depending on, the country that we are talking about. But yes, I mean, I think that, so for in the US context, it's been shown, and again, it's not even our work, it's been shown in the past that, the data that you feed into the model has higher volumes for certain groups. And so what the model does is just, replicate those higher volumes. And so, if you use the past to predict the future, basically you are translating the past into the future. That's what the models do. They don't do any miracle. And so, I think that it's important to look into those biases before actually inputting the data into the model. However, the challenge there is not so much knowing that, your model outputs something that is unfair, but actually how to correct, the impact of the data bias in the models. And that's what, the second project tried to do. How can we model how the underreporting is happening, and how can we incorporate in a model that predicts crime? There's other researchers that argue that, like the problem itself, like the crime prediction problem, shouldn't even be tackled with machine learning algorithms, right? Because it's just kind of providing another tool for this bias to be perpetuated. In my group, we think that it's a relevant effort to see if, the data sets that are used for the training could be improved, because, there's still going to be police departments that are going to be using this type of tools. So at least, if the data that they input is less biased, that would be an achievement.
Yeah, absolutely. And that actually brings me to the another question I had. So you were, I'm assuming this project were in collaboration with external partners. So I think, so what were the challenges, but also the benefit of working with such a real world context, let's say, and also with the external partners in this project, but also generally in your work?
So are you asking about the role that external partners play, or?
Yeah, but well, more specifically, actually, what kind of, so for example, here you were saying that, well, police department will be using a certain machine learning approach anyway, but maybe giving not enough attention, not paying enough attention to certain elements. I think that in other kind of maybe less research intensive contexts that still have to, well, that probably have that decision making, well, are responsible of the decision making bit. Some of these things might be missed in a way. And so I was just thinking, what do you think could be the role of research, particularly when so linked to this real world context?
Yeah, I mean, I think that, so not only for the projects that I have discussed today, and for many of the projects that we work on, we just think of them as, just another data point. Like, I've never thought that, the analysis that we do or the tools that we build are just a substitute for any type of decision making. They are not. What we do is that we just provide additional data points that could be potentially helpful and used in whatever, decisions are being made. AI solutions, or data science solutions, so however you want to call them, are not perfect. They come with a fair amount of errors and the lack of accuracy that we try to measure as much as possible. But human decisions are also not perfect, and so we just think of our solutions as hopefully informative data points for policymakers. Again, we don't think that it should just be whatever the tool that we build says should be the final decision, but it might inform, and it might be helpful overall. So and that's been the approach, as I was saying, for the, the socioeconomic maps that we talked about at the beginning, for example, right, that we work together with the World Bank. I mean, that shouldn't be just the thing that's used to decide, where do you set up a school or a hospital at all. But, if you have, say, census data from 5 years ago, and then you have these data points, and then you have information from the community, and then you have information from other partners that you might have, then you put everything together and make a decision. So I think that that's, if, any type of organization aims to use tools based on data or on insights extracted from data, I think that it should just be used with caution and just as another data point.
Yeah, right. Cool. Is there any question from the audience? I actually, well, just a quick one, just because you mentioned this on socioeconomic prediction, and I found that project very interesting as well. Was that on a specific country, or because yeah, I think there was one specific country mentioned that, but it just went through that very quickly. So
yeah, so that one was done in Mexico and in Guatemala, because those were the two countries that, I mean, that our collaboration with the World Bank was interested in. So it was done in two countries. Yeah, with cell phone data.
Yeah, because probably is also area where you don't have that many official statistics.
Yeah,
right?
yeah, like, yeah, in Guatemala at the time when we were doing the project, censuses were being collected, if I remember correctly, every 10 years. So, you know, it's a long time. And again, the proxies that we were offering, using, for example, aggregate information, the accuracy was around 75%. But still, I mean, it's better to have a noisy data point than no data points. So again, you know, there was the main value of that project is that, you know, if you're going to be 10 years without a census, maybe having a proxy and being aware of the errors associated to that proxy information might be more useful than not having anything. Yeah, so yeah, that was the idea.
Absolutely. Okay, I think that if there are no more questions, some people had to leave, unfortunately, a bit early. They're thanking you anyway in the chat. Very inspiring talk. Yeah, I mean, that was fantastic, really, Vanessa. Thanks a lot for sharing your very interesting research. And yeah, thanks everyone for staying with us. And
thank you again, Alessia, for the invitation. I really enjoyed giving the talk, and thanks everybody for attending the talk. My email is somewhere there in the slides, or you can Google me. I'll be happy to, you know, answer questions, talk about research with anybody who's interested. So just ping me.
Amazing. And the presentation is going to be uploaded on YouTube, so you can always go back and listen to it again. People are thanking you, Vanessa. Again, thank you very much. And
thank you, guys.
Yeah, I think hope to see you soon.
Yes.
Online, probably, because practical distance, but yeah.
Okay. Thank you, everybody. Have a good rest of the day. Bye.
So, bye-bye.